Welcome to this week's edition of Post Clouds, the podcast, where Stephen and I are going to be talking about the cloud technologies, what next, what problems we're encountering, and so on and so forth. My name is Chris Krantz. I'm a bit of a cloud guy, a self-described cloud guy. Been in the industry for a while and love talking to my co-host, Stephen.
Hello, Stephen Howell. I've been a sysadmin, engineer, architect, designer of various systems, cloud and pre cloud. Today, we're going to be walking through some of the infrastructure issues that people might have to deal with, but often get wrong footed by. And we're going to be looking at specifically layer 2 and where layer 2 lives today. We're going to be talking about things like link aggregation, how to make your networking resilient, some of the pitfalls, the nice little benefits, and kind of track how people have solved these problems.
Nice, looking forward to it. This is a topic that I think takes me back a long time ago. So I started kind of my grown-up IT career with technologies like VMware and NetApp storage. And I remember my first encounter of this as a challenge. So you've got a bunch of servers with a bunch of network cards in them. You've got some storage arrays with, again, a bunch of network cards in them, assuming we've got some network attached storage. I guess the problem here is I want to make the most of all those network interfaces. They could be 1 gig, 10 gig, 100 gig, whatever they are, whatever performance they are. I want to get the absolute most out of those without compromising resilience. So I guess this is the challenge that we're talking about here. Is that right, Stephen?
That's correct, yeah. And I first encountered this problem probably a little ways before VMware. I remember being delighted when we were able to use virtual PC in our demo environment to run VMs in the DMZ, no less. I really came across this problem and its solution when we were running our DNS, and we wanted them to withstand the failure of a network link. And how do you do this? Well, you go online and you start looking at these options and you find out about all these mythical networking terms like ether channel and link aggregation and control protocol and link aggregation groups, and everyone seems to have something different. And you sit down and, in my case, get shouted at by a guy with a very upper class accent who occasionally rattle on about blunderbusses and frequently tell me I was doing things wrong. So I spent a lot of time hitting the books learning this one. Come VMware, we kind of got it introduced into the virtual environment. And this whole set of technologies is designed to make that single vital cable between your server and the switch a bit tougher, just in case you break the cable, in case your network card breaks, even in more complex situations, in case you need to power off one of the switches and recycle it. Maybe you need to update switch firmware and you need to reload the switch, or you have a power failure on the switch. You can get into configurations where your single server has two cables, and those two cables could even go to different switches. But from the perspective of that virtual machine or whatever the workload is on the server, it is supposed to look like you've got one single cable. You're pushing that complexity down the stack, and at the top of the stack, your application sees a never broken, perfectly performing, perfectly resilient environment. It's what everyone always wants, right? Yeah, that's more or less what we're looking for.
You need that because most applications you can't say talk to this server. It's available on 5 different IP addresses. Although you've got things like DNS round robin, that doesn't really work for session data, does it? So I guess the idea there is I want to be able to use more than one physical interface, which is traditionally see them as a physical interface has a physical IP address and a MAC address, and that's how I address that server. I guess now we're saying we need to be able to group all these together to have a single identity, so I can still address that server, but now I can leverage all that bandwidth, but still have a single identity.
And the stuff below that makes all that IP traffic happen is the layer 2 domain. So we're going to be talking a bit about what happens in the layer 2 domain here. And normally, when you advertise a MAC address, you have the ARP process, which is just a broadcast to say, hey, who's got this IP address? And it'll come back with a MAC address. And that MAC address is specifying a single network card. And that's what normally happens. It's the way the system was designed. Well, we're going to be talking about how we can fudge that so that when I ask who's got this MAC address, it can point me down multiple network cards.
So you mentioned layer 2 a couple of times. I'm assuming we're talking OSI 7-layer model there. But just for anyone who hasn't come across this kind of terminology before, if you want to go look up the OSI 7-layer model. But Stephen, can you just quickly describe for us what that layer 2 is and kind of what's layer 1 and layer 3 kind of to help sandwich that together?
Let's do a sprint off the blocks, right? So this model takes your network connection, it breaks it into different layers. As you go further up the layers, it becomes more abstract and closer to the application. The bottom layers are closer to the physical hardware. Layer one is looking at the physical and electrical signaling that makes stuff happen. Layer two, we're talking about Ethernet for the most part in modern systems, right? Layer two is what allows an endpoint to send a frame of data to another endpoint. We're not talking about port numbers or addressing or anything. It's purely one network card at a hardware level, takes some data and squirts it off, and it's received by another network card at that hardware level. And that uses MAC addresses, media access control addresses, which are burned into the ROM of each network card and provide a different ID. And each vendor has a block of them. Every time they sell a network card, they increment a counter and burn a new address into it, and off they go. And that gives us a way of sending pretty dumb data. It's just like data is on wire, goes to this one, maybe it receives it, maybe it doesn't. It's just like a fire and forget system. And then we go up to layer three. We're running now at layer three over IP, and we can run TCP on top of our IP as well. And then we go up above that, and you start to look at connections, connection oriented methods, which is like opening a port and keeping that open for the duration of some signaling. Most of the time, when you're looking at Nginx and these other things, and you're running web traffic, you're up in the layer three world at least, and maybe what we call 4 through 7, which is just like HTTP routing, basically. HTTP routing and proxying is 4 through 7. To actually make it work, you still need those bottom layers. And if you want to make your single physical cable be resilient and tolerate failure, then you need to fudge with layer 2 or layer 3. And because this all started with quite meager cost hardware, very simplistic, very small chips, the lower you go down that stack, the less horsepower you need to do everything. So the first place that people were able to put any resilience into the system was at layer 2. Layer 2, you can do some really basic hardware tricks and make it look like two network cards are actually one network card, assign a virtual address to them that isn't either of the network card's real addresses, and create a channel that isn't a real physical channel, but is a logical channel consisting of multiple underlying bearers. And that's what we're looking at. We've got link aggregation control protocol.
That's the topic for today. So LACP has been ratified as a IEEE standard. That's what we're looking at here from that link aggregation perspective. That some people might call it network bonding as well. We kind of covered some of the purposes for what LACP is used for. And I guess just to pause there, do you say LACP or do you say LACP?
I've always spelt it out as LACP. People say lag as lag instead of LAG, but
I've experienced different places, and I always kind of adapt to what people use themselves. So let's stick with LACP for today. So what are the different kind of modes and the standard configurations you see with LACP?
yeah, so one of the reasons that this is kind of a painful area is, like many things in networking, this was first used by a vendor, and then it became more widespread and was ratified, and a generalized standard was adopted sometime later. And even though this was 20 plus years ago now, we still have to deal with this kind of mishmash of vendor specific and general standard. So in the 90s, Cisco acquired Carpana, and that brought this Ether channel standard. Now, Ether channel is the kind of precursor to what you said the IEEE standard was, and it was a static. I am always going to have X number of links, and I'm always going to combine them into a single Ether channel virtual link. Right? It's a very dumb thing. You need to hard configure both switches. You have to agree on the ports in advance, and if one cable is pulled out of a static Ether channel, then that proportion of the traffic is going into a black hole, which is bad. So if you have your static Ether channel and one cable gets pulled, then oopsie, you might just black hole half the traffic. So you're increasing the bandwidth, but you're not providing resilience. And that wasn't what a lot of people wanted, understandably. They didn't just want to increase their 100 megabit connection into 400 megabit. They wanted to actually have some degree of tolerance in there, because otherwise, if you wanted to reset your switch, your administrator would have to go in and manually reconfigure the switches and hope that no traffic would be dropped while they're reconfiguring them, and then take one link out of the bond, faff around with the down member, and then bring that link up again. and it was a lot of work. About 2000, this was ratified. We've got the Institute of Electrical Engineers. I forgot what the other E is. So 802 is where all the Ethernet stuff lives since time immemorial. You've probably heard of it in terms of Wi-Fi. 802.3 AD in the year 2000 took Ether channel and standardized it into a protocol that could work not just in a static configuration as Cisco originally envisaged it, but also in a kind of dynamic configuration. It does this by broadcasting Ethernet frames. So it's got what they call LACP PDUs, and it's got to broadcast these alongside all of the other traffic as beacons to say this link wishes to run LACP. And if two switches are both sending them, then the instant that they start receiving ones from the other switch, boom, the link is going to come up and it's going to start forming part of this virtual Ethernet link with multiple underlying cables. This signaling and the announcement of the links fixes the problem with static Ether channel in that the links are now aware if the signaling stops and they're not hearing their neighbor anymore, they can tell that the link has gone down. So they can then intelligently remove that cable from the virtual link and traffic isn't sent into a black hole anymore. Wonderful. Lots of problems solved there. The choice of how you decide which link to use is a thorny one. This is where a lot of these problems occur because you might think, oh, well, I've got 4 cables. That means my connections are now going to be 4 times as fast. And at a gross net scale, that is true, right? You do have 4 times as much overall bandwidth. And if you've got a web server, you're going to see 4 times as much traffic being able to traverse that link. But if you've got a single large file copy going on, then what needs to happen is you need to be able to say one packet go on one link, then another packet go on another link, then another on the next, and another on the next. And the way that you make the decision of which link to use is to do what we call a hashing function. You take some specifics about the data that you're going to send and you use the specifics that are observable in the header of that data to decide which link am I going to put it on. And you've got say 4 links, then you use a hash function with like a modulo 4. So it just counts 1, 2, 3, 4, 1, 2, 3, 4. It's only got 4 possible outputs. And to start with, the switching was done based on the MAC address. If I've got one server over here coming into a switch, talking to another server over here on the other switch, then the hashing of the MAC address would always yield that traffic going down the same link. If a link is removed from the bond, then it'll move on to a different link via the hashing algorithm. But if I have a single large transfer, it's always using the same link, right? Which means if I've got gigabit links and I take 4 of them, my single large transfer is still running at 1 gigabit, which is annoying. And this is just a property of LACP. It's not going to give you generally increased throughput on a single transfer. You can do some funky stuff that isn't quite part of the standard, but in general, standard specific terms, you can hash based on the MAC address. You can hash based on the IP address at each end of the connection and the port number at each end of the connection. But beyond that, your options, if they do exist, fall a little bit outside of the actual LACP standard. Yet you don't get anything for free here. If you want to run at 100 gigabit Ethernet, you can't just take 10 gig links and join them together. You're not going to get that.
So LACP, although it feels like you're bonding these interfaces together, you're not. It's not really a load balancing. It's not like a application delivery controller or a proper load balancer. Primarily it's about the resilience. You get some side effects of some increased bandwidth depending on the workloads. Which is nice. I think that's some of the misunderstandings I've seen in the past. Connect up all these servers and storage and all the rest of it, and then people are saying, "Oh, look, but I'm only getting 1 gigabit of throughput." Yeah, of course you are from a single machine. So are these problems that kind of change at scale, though? My experience with a lot of these is quite small networks where you've got a single, maybe 2 racks, and you've got some top of rack switches, and it maybe goes to a single core. And I guess what we've seen over the past 5-10 years is a movement from traffic where I've got a single server or a single group of servers that go outbound talking to my users and the internet and so on, And now that we're adopting microservices and distributing these systems out, I've got a lot more sideways network traffic. Now that's fine in an environment where I've got just got two racks and top of rack switches. I'm guessing this is something that's a challenge as you scale that out. Now I know, Stephen, you've worked a lot more in the enterprise in large scale deployments and stuff where you have much more complex network designs. Is this something you've kind of encountered where you have to rethink the design because it's a very different network model, or is it just the same challenge, just in a slightly different way?
Yeah, I think there's an element of that, absolutely. And as we go forward, what we tend to see is businesses end up with more and more complex networks over time, where we would have a hub originally that with a couple of things plugged in and it was enough for an enterprise. You move forward and now you've got some VLANs appearing, you've got spanning tree protocol. Then you start to concentrate things even more. You're running link aggregation protocol to just a couple of core servers, and then link aggregation protocol to everything. And then you maybe want to double down on that. You've got some blade chassis, you've got larger servers, you've got maybe two switches at the top of every rack. You need to consider port channel, virtual port channel, as Cisco calls it, which is link aggregation, where two switches behave as one virtual switch, if you like, and you connect to two switches and pretend that that is one physical cable. And you get to the point where when you start layering lots and lots of switches into an enterprise, as you put virtual machines in, and those virtual machines have virtual switches, and then the virtual switches become more sophisticated and start to behave like enterprise grade real switches, then it looks like your network scope has suddenly multiplied, because where you did have a couple of servers connected to switches, each one of those servers then becomes like its own mini switch with its own bunch of clients hanging off it. And all of a sudden, you've just got a lot more network traffic. And in particular, with layer two, you can end up with loops. You need to worry about that. Make sure that you don't plug a loop cable into one layer two broadcast domain, because that's just going to nuke everything on that domain. And be careful about broadcast traffic. That's traffic that's going to the entire layer two domain. Unknown unicast, where you don't know the MAC address and you've got to figure out that MAC address. And multicast traffic as well, that's going to everything there. And those are very difficult when you get large layer two domains. And this is the kind of reason why you don't see a lot of like Apple Bonjour stuff, Google Chromecast and others running on very large networks, because they can kind of take over the network.
Yeah, I guess these are different protocols and applications that they advertise to every single device on the network to say, "Hey, I'm here, and this is what I do."
But not just they advertise to every other device, but they expect the devices that acknowledge that advertisement to talk back to them. So it like elicits this feedback loop across the network.
It ends up being one of those misconceptions. I've got a 1 gig network link. I should be able to use 1 gig's worth of data transfer. And I guess people misunderstand that there's so much extra noise, usually useful noise and intentional noise, where there's so much additional stuff that happens on the network. Sometimes you actually get quite a small fraction of your potential bandwidth. And all the things we talked about here with LACP, virtual channels, and even some of the virtualization stuff from VMware and stuff just adds more metadata to every single piece of traffic you send. So your network becomes incredibly complicated.
Yeah, and so we see these kind of layer two concepts. While they were great in the 90s, they've become really strained. And trying to use layer two right now is you're kind of going out on a limb. That the worst architecture I've ever seen, and loads of Cisco guys can back me up on this, is stretched layer two, where you have two sites, maybe like Birmingham and London, and you decide that you're going to have the same layer two domain present in both, because that's going to be really easy to move your virtual machines. So it's going to be super easy. You can just like migrate them over there. You've got two like storage systems that have replicas, and yeah, it's going to be fine. But what you're letting yourself in for there is this kind of unknown response time for all of your broadcast traffic that locally might take under a millisecond, but over that link you might have to wait like 20 milliseconds for a broadcast to go through. And anything that goes wrong at any point in that link can completely torpedo either end of the link. It's terrible. It's a really, really, really terrible concept. So the way that things are slowly going is, well, much like that, but we move away from layer two. We provide layer two as this comfortable furniture that a virtual machine will see when it gets on the network. But actually, we're not trying to carry layer two everywhere. on the actual network. What we're doing is we're carrying layer 3, and we take that virtual machine traffic and we wrap it in something else, we tunnel it, VPN it, whatever you want to call it, it's encapsulated. And that encapsulated packet can then be, instead of switched, can be routed at layer 3 and placed wherever we want it. And this enables us to do a lot more tricks, if you will, and more scalable tricks, the kind of tricks that let the internet run. So instead of taking the concepts that were used in companies and small enterprises and trying to scale them up to the scale of the internet, what we're doing is we're taking the technologies that enable the internet to run and we're bringing those into the enterprise and down into the small, medium businesses now, even, so that we can do a lot of throughput, and we can make use of the fact that switches, which used to be hubs and then became switches and then became managed switches and then had some basic routing on them, those chipsets now can do a lot. They can do far more than your home router can. They can absolutely create mesh VPN style networks. They can do like BGP peering and all this stuff. And so we kind of make use of that. And the servers, because they're all running virtualization workloads, well, they can do all the stuff a router can as well. And certainly the core infrastructure has been able to do that for years. That's not a problem. So we change gears, and instead of being so obsessed with layer 2, start treating our little in-house network more like the internet. And this is what the cloud providers have been doing for years. This is how you can have your Coca-Cola and your Pepsi traffic coexisting without seeing each other, right? They're all encapsulated and separated, and they're not stuck on just a dumb layer 2 channel.
So this is kind of a recurring theme somewhat, in that the people that need to know and really understand layer 2 traffic is kind of shrinking, because you don't really need to know it anymore. You've got these, like you say, these overlay networks, and you've got that abstraction layer that I see in the cloud. If I go and fire up an instance in AWS, I don't need to care about this stuff. I might need to worry about my VPCs, which are not virtual port channels, as you see in Cisco terms, but they like to use the same acronyms. But I care about things in a different way. It looks like I care about things in a layer 2 and layer 3 level, because I'm still talking IP addresses and so on. But it's so far abstracted from me that all this intelligence is going in there. I wonder how much kind of layer 2 is becoming a kind of a lost art, and whether there's any need for that to be an art anyway, because you could end up having all of this virtualization and all this intelligence baked natively into the switches, and it just comes a click, click, next, finish configuration of this anyway. Do you think we'll get to that point where layer 2 is abstracted from 99% of IT users and network admins?
I hope so. I think we're slowly getting to the point where a lot of this was gated behind vendor-specific toolkits, and with the help of projects like free range routing, an open source project that started at Cumulus and has been open sourced, these are enabling lots of people to go and do this. Of course, everyone still needs a plumber, so I don't think it goes away completely. You still need the network plumbers. There's got to be someone that sets this up and manages it, but we're getting to the point where things that were gated behind $100,000+ licenses on very expensive high-end hardware have steadily been commoditized over the past decade or more, and are now available to people. And it's just a matter of time before we get from them being available to everyone to being automated and templated and easy to use. And there is just an easy button you can click, and boom, there you are. That's what I hope we're going to see in the next couple of years.
I've never managed to get my head properly around networking, so I'm all for that as well. Now, as a bit of a public cloud guy, is this something that goes into the considerations when looking at public cloud, or is this really in the realm of kind of private cloud, on-prem, very advanced home office setups and those sort of things?
I'd say with public cloud, you need to be concerned more about routing protocols for our American listeners. Layer 2 isn't as much of a concern. If you are getting data in and out of the cloud, then you're probably going to do it over some VPN link, and you will need to consider how Layer 2 behaves. Certainly, if you're trying to have an endpoint in your office and communicate with the cloud, or if you're having to talk, say, to a payment provider who has their own hard endpoint with a credit card agency and things like that, it becomes more relevant. In terms of use cases for this as well, that while public cloud is awesome and you can flick that lever and you can get the capacity right there, what this can be useful for is if you've got, I need to keep hold of, say it's a couple of terabytes of data that you just want to store forever for whatever reason, You can do that very cheaply on-prem. You can have a little office with a server in the corner that has your 20 terabytes of data that you just need just in case. And it's going to be a lot cheaper to keep that thing plugged into the wall than it is to run a public cloud storage facility. If you understand layer 2 and you understand how to interconnect these things, you can run a few little servers and you can have them nice and resilient and sipping the power in the corner of your office, not really costing you anything. And you can spin up those compute workloads at massive scale in Amazon when you need to, and make the best use of your money. So I think it's useful to know.
We touched on this last time, and I think it will be a recurring theme. Just the idea that you shouldn't have a cloud first or a container first or whatever first policy out there. It should be a what makes most efficient sense for this workloads. We're also seeing a lot of people much more interested in green technologies and what the most efficient use of the carbon footprint I need to leave. And often that's going to be on-prem, that's going to be in efficient data centers, you properly using renewable resources and so on and so forth. Understanding this stuff I can definitely see is really important, because where you've got those on-prem or co-located workloads, they're going to need to be plumbed in and resilient and probably decent bandwidth as well.
I want to see the end users, the people out there, empowered to make whatever decision suits them and not get railroaded into someone else's business plan at the end of the day, right? If you've got all these tools at your disposal, you can go and buy some systems and set them up and put them to use. And you don't need to pick from the expensive public cloud offerings if you don't want to. So it gives you an element of choice. It's always good to have the tools at your disposal.
Feels like that's a bit of a takeaway, but anything that you kind of want to summarize from today and give people as kind of key takeaways that they should be able to understand from today's discussion?
The main point here is link aggregation is great. It lets you pass more traffic, but it's not a free lunch. You're going to have to do some reading, figure out what happens if you lose a link, make sure that the way you've set it up, and there are many ways to set it up, pick the one that suits your use case, make sure that your switch is compatible with the one you choose, make sure that if you want to be able to withstand link loss, that works before you put a live production workload on it. Be aware that it's not going to just multiply that bandwidth for a single large transfer. If you've got a web server and you've got hundreds of clients hitting it, yeah, you're going to see a scaling in bandwidth. But if you've got one big file copy going through, you're still going to be limited to a single link throughput.
I just reiterate the point of make sure you're testing this stuff and test it more than just one system, because the way that these aggregation protocols work, if you've just got two things talking to each other, you may not be testing the full extent of those multiple interfaces. So make sure you're testing this at scale. It doesn't need to be massive scale, but at scale enough where you can see those different interfaces being used, and go up and unplug some stuff. I always used to enjoy that. So literally, that's the best way of testing stuff. Take it out of the switch.
Just don't be that person that waits for the DR test to find out if it works, right? Do not be that person. We've seen that person. They do not have a happy life.
I love today's discussion, Stephen. It was a lot more deep dive than I think we've been into before. I love doing those technical deep dives. As much as I'm not necessarily as technical as I used to be, I really enjoy that. Thank you for kind of explaining some of that detail around this. It feels like a really complex topic that we could probably talk about for a couple of hours and get into a fair amount of boring, mundane detail. Hopefully we've kept it a little bit more lively than that.
Because this is such a deep technical topic, we're going to put some links in the video. You can look at the links below. They'll come up in the podcast notes as well, and you'll be able to do some further reading on this. It's an interesting topic. It's a useful one. I don't think we've done it justice in the time that we've got here, but I hope this is of use.
Hope you enjoyed today. If you're watching us on YouTube, don't forget to like and subscribe and all those things. Just helps us know that you're enjoying this content. If you're listening to us on Apple Podcasts, Google Podcasts, Spotify, whatever, again, hit the bell icon to subscribe, and hopefully we'll get your feedback. Hope you enjoyed today, and we will speak to you again soon.